Okay, so hi everyone. This is Chijao and I'm Wei Hao, and today we're going to talk about the algorithms involved in image compression. So before I start, let's talk about the two different types of image compression. There is lossy and lossless. So what lossy means is basically some data is lost when you compress an image. So for example, like if your image has maybe different shades of red, but those shades of red are very close together, then they will be stored as the same shade of red. So if you go through a lossy compression, you're actually losing some of that color density inside your image. Whereas for lossless compression, every shade of a pixel is stored as is, so you're not actually losing any data. So today we're going to go through the algorithm involved when it comes to lossless compression. So let's go through some assumptions before we go through the algorithm itself. First of all, we assume that each pixel in the image takes up 8 bits. So for those of you who don't know, a bit is actually a binary digit. It's like can either be 1 or 0. So if we assume that each pixel in the image takes up 8 bits, which means that if you store one pixel by itself, it will be a sequence of 8 digits, which is either 1 or 0, which means there are 256 combinations. So there's, in our example, we assume that there are only 256 colors, but of course, in the actual scenario, each pixel is stored as an RGB, so there's actually 3 numbers you have to store for every color. Okay, so some examples here will be, for example, white will be just all zeros and blacks will be all ones, for example. Okay. So this is the image that Chija and I came up with. So it's basically 100 pixel image. So there's 10 by 10. So if we were to to calculate the size of this image, it will be 100 pixels times 8 bits per pixel, which makes it 800 bits. Okay, so now we want to compress this image using Huffman's coding, which is a lossless image compression algorithm. Okay, so step 1 of the algorithm is actually to find the frequency of each color. So, and put them in order. So in this case, the blue will take up 62. We have 62 pixels of that color, and then the next one will be 20 pixels of green and so on. So we have that list. And then the next step is to form what is called the Huffman tree. So in this case, we have the different colored pixels in order. Then we take the bottom 2 pixels and we add them up. So the pink and the white, we add them up to make 2. And then we move these 2 back into the list over here. So you can see those 2, the bottom 2 is replaced with the white here. And then we keep repeating that process. So the next iteration of making this Huffman tree will be taking the bottom 2 from just now, 3 and 2, and then add them up together to make 5, and then put it into this sequence here. So because 5 is greater than 4 and 3, so 5 is moved further up that list, and then we'll keep moving on. So same thing, 4 and 3 make up 7. So then the 7 will be sliced back into the queue, so to speak. Okay, so after everything, we will end up with the full Huffman tree, which is here, and then of course all will add up to 100 because there are 100 pixels in total. So now I'll pass on the time to Chijao, who will explain how the compression works after this step.
Hello. Yeah, okay, so the next part is the compression stage. Okay, if you can see here, so now we will map each color to the path that you will take. So if you can see the blue over there, okay, the path it will take is the right side. So in our code, we will code the blue as 1, right? So for green, it will be 0 because it moves to the left first, then move to the right. So it'll be 0, 1. So we do the same thing for the rest. So anyway, look at this tree. It isn't very balanced. So maybe can someone tell me what is the problem with this tree if let's say it just keeps growing one-sided? Does anyone know? Like, okay, so the first one, right, I will just store as 1, so that's a 1 bit. The second one, right, I'll store 0, 1, so I'm taking 2 bits of data. Okay, as you move further down, what is the problem that you can foresee if let's say this tree continues to be one-sided? Does anyone know? Okay, anyway, yeah, so one of the limitations is that if let's say the tree keeps going one-sided, right, the amount of data I have to store actually might even reach more than 8. It might reach like 10 or 20, but it will still result in a compression overall because the frequency at the lowest part of the tree will be the least. Yeah, so that's one thing to take note. Okay, so this is how after that you would store the tree. So for the yellow, right, is 001. So you store as the data is 001, followed by another 0010, and then it'd be 110010, 0011, and all the way, right? So that's how the new compressed file will be stored. Yep. So after doing all the calculations, right, from the 800 bits of the original data, now you only store as 181. Okay, but of course, in addition to the 181, which is just the mapping down the tree, we still need to store the tree data itself, right? But overall, it will still be lesser than the 800 bits. Okay, so when after the bit is compressed and stored, right, it will be just stored as all the individual binary itself. So how the tree would search to decompress the image, it will go down, it will look at the tree, and then it will decode each one individually. So for 0010, right, we'll go down the tree, 0, it will move left, another 0 will move another left, so it ends up at here, and then it will move 1 and 0, so we know it's a yellow. So we just do that for all the images, for all the pixels. Yeah, so you see here it will be yellow, and then subsequently it will form the image. So as you can see, this technique, it doesn't lose any data. It's just a more efficient way of storing the data. Yep, so as mentioned earlier, one of the limitations is that it might result in a one-sided tree. Yeah. And then also, because it is a lossless compression, it is also not, it will not compress as much as what a lossy compression would be. So as Wei Hao mentioned earlier, like, because our human eye, right, does not take into account the different shades of colors very accurately. So some of the developers of lossless lossy algorithms, right, they will actually try to remove some of these pixels which our eye don't really pick up, and then just treat it as the same. So that will result in a higher compression ratio. Yeah. Yep. So that's our end of our presentation. Thank you.